Hi, everyone. Thank you all for coming here at this late hour of the day. My name is Gal Diskin, and as was said, I will be presenting about virtualization security. The purpose of my talk is to introduce to you the low-level mechanisms that are related to the infrastructure that makes the virtualization secure and basically allows us to use virtualization securely. So who am I? Why am I talking to you about this? The key point that is related to virtualization here is that I used to work for 8 years for Intel, doing a lot of the infrastructure work on virtualization security. OK, so let's move on. I want first to give a few thanks. I want to thank my wife right here, who's been taking good care of me while I'm doing research. I want to thank everyone at Cyvera, and especially the people that reviewed the talk for me. And all the security people at Intel, greets to you all. You know how it is from the other side now. OK, so what am I going to talk about today? I'm going to talk about hardware-assisted virtualization. I'm going to talk about the software stacks and different virtualization approaches and weaknesses of each approach. I'm going to talk about the complexity of memory management and the related weaknesses that this affects on virtualization. And finally, I'm going to talk about the computer platform internals and why those lead to certain weaknesses in the implementation of virtualization platforms. And as a special bonus, I will show a small potential VM escape that might work and might not. No demo, sorry. Kind of broke down my computer when I tried to do it. Anyways, so what is virtualization? In the context of this talk, virtualization is replacing the real hardware that you have, the CPU and the computer platform, with a virtual environment. Historically, we can trace the roots of virtualization even to Alan Turing and the universal Turing machine concept, which was basically a machine that could emulate any other machine. After that, at the late 70s, Popek and Goldberg came up with the virtualization requirements for computer architectures. Anyways, so that's where we start from. A bit of terminology, just so we're all speaking the same language. A virtual machine manager, or VMM, is the software virtualizing privileged instructions and the hardware. Basically, this is the core of the virtualization system. A virtual machine is the software stack running under a VMM. A guest operating system is the operating system of the virtual machine. And the host operating system is the operating system that is controlling the VMM. And root operation is when you execute within the VMM. So first question we need to ask ourselves, this guy is talking to us about secure virtualization, but there are many definitions of secure. So what is secure virtualization? So the security goals that we need to define what are our security goals when we want to secure our virtualization platform. So first goal is preventing modification of the host operating system by guests. This makes sense, and naturally also the VMM has to be in order for this to even work. You need to prevent one guest from changing another guest, right? If I have two virtual machines, I don't want one to attack the other or vice versa. You need to prevent the guest hardware, the virtual machine, from actually subverting the hardware or firmware of the system. You need to prevent the guest from stealing data from other guests, from the host operating system, or from the VMM. You need to prevent denial of service by a guest OS or getting unfair share of resources relative to other guests. And you need to keep the guest OS secure. You don't want to downgrade the normal security mechanisms of the guest operating system. Now, this may not be equal in every platform. For example, micro-virtualization usually gives access to the guests directly to the hardware, which is a very bad idea in security terms, but this is what they do because they want the virtualization capabilities for monitoring. Other micro-virtualization engines are used for instrumentation, and they, again, don't care about security. But if you care about security, you shouldn't give access to the hardware. And we'll hear a lot about this later. So moving on to the first section of this talk, I'm going to talk about the different software stacks or different ways to use virtualization capabilities. So first one we have here is the type 1 hypervisor, also called the bare metal hypervisor. It's important to note that this is sort of a simplified view, but it's still, it represents most of the way the system works. So what we have here is, first off, we have the processes. The processes each executes in a different guest operating system. The guest operating system is executing above a virtual machine monitor or a hypervisor, and this one is executing directly above the hardware. And between each one, we have the different interfaces. So as you all know, between processes and the operating system, you have system call interface. And the interface between the guest operating systems and the VMM, whether they are aware that there is an interface or not, is the VM exits and VM entries. A VM exit is the transition from the VM, from the guest, to the VMM, to the root execution mode. And the VM entry is the opposite, transition from the root execution mode to the guest. Now, one of the key points here is that the bare metal hypervisor has to virtualize every access to the hardware. So basically, it is emulating all the hardware accesses. This means that this creates a very large attack surface on the actual virtualization implementation. Next off, we have the type 2 hypervisor. So type 2 hypervisors basically are hypervisors that are executing inside the operating system. If type 1 is things like VMware ESX, if you're familiar, while type 2 is things like VMware Player, which executes in a manner similar to a program. And we have here guest operating, the processes, the guest operating system executing above a VMM that is inside the OS. Now, the interesting thing here is that this type of virtualization engine is actually using the drivers of the host operating system to interface with the hardware, which means that requests, for example, to draw on the screen from the guest operating system or to access the graphics card pass through the VMM to the host operating system, which creates a different attack surface of the actual communication. In some cases, these actually use what's called para-virtualized drivers, which are drivers that are aware that they are running in a virtualization environment and are calling directly to the OS, which naturally creates a whole new attack surface. You're too quiet. Are you still with me? Good, good. Let's see. Which program is this one, the one I'm pointing at? Come on, one guy. Ida, who said this? Well done. OK, now you're with me. Let's go. Let's move on. OK. So as I mentioned, there are a lot of challenges when you want to emulate the ISA, the instruction set architecture. And the VMM needs to emulate every instruction or event that it registers on. So the VMM must register to certain events. It's not the same in every virtualization architecture, but I'm talking about the Intel architecture. That's what I know, as I told you earlier. And in Intel architecture, there are things that are called the fixed one exits, events that the VMM has to exit on. It has no choice about this. In addition to this, in any case that you have other additional events that you want to actually virtualize, then you need to exit on those as well. So there are lots of challenges when you come to actually emulate the ISA. First off, you get the problem that you need to know the exact specification. Has any of you opened the Intel SDM software developer? Well done, guys. Just for paying attention, here's one. Anyways, the Intel SDM is like 8,000 pages, I think, now. And while instructions are fairly documented in one place, architectural events, such as interrupts or other events, are documented. You have to read the entire manual to actually know how they work. And even then, it's uncertain that you will get the actual description. So specification is not very simple, and handling the corner cases is very hard. Deciding if the guest has the right privilege from root operation is also fairly complex. And this leads us to situations which are called confused deputy, where you actually have more permission in the root operation than the guest would have had if he executed it normally. And you do an action on behalf of the guest that is too much. And that's the reason for this guy over here at the top that is definitely a confused deputy. OK. So what's next off? When we talk about software stacks, one part of the software stack that we didn't discuss yet was the system management mode, or SMM. System management mode actually runs in parallel to the other operating modes in the machine. So that means that while you're executing at any given moment, whether you're in ring 3, ring 0, or in the virtual machine monitor itself, an SMI interrupt, which is the interrupt that causes transition to the system management mode, could happen. And this creates an attack surface. For example, the SMM cache poisoning attacks that were popular about 7, 8 years back were basically this type of attacks that an attacker within the guest operating system could do to infect the SMM. Now, the interesting thing about SMM is that while the SMM has unlimited access to everything on the right-hand side, or left-hand side from your point of view, wherever, the virtual machine monitor or any code that is executing on the other side can't access code that is executing in SMM. So basically, if you infect SMM, you can infect anything around here. Now, what you should be asking me is, if this is such a big problem, why isn't there a way to virtualize SMM? Right? Or there should be a way to virtualize SMM. So the answer is, there is a way to virtualize SMM. It is called SMM transfer monitor, or dual monitor, or parallel monitor, or whatever you want to call it monitor. And basically, it is meant to be used to virtualize the system management mode. Unfortunately, has any of you heard about it in use, in practice? I can tell you that I know of one 3-letter government agency that is using it. And no other organization that I've heard of is actually using SMM, STM. One other interesting quirk about STM is that the people that are actually meant to implement the STM, the transfer monitor, this part, the virtualization for SMM, are the hardware vendors, the Dell, the OEMs, Dell and Samsung and whoever and Sony and whoever builds your computer, not VMware that is making the VMM. And so it creates a whole new complexity because they need to decide on the interface. The STM is talking with the VMM and vice versa. So this is a very complex architecture that doesn't really work, and SMM is just not virtualized. And we all hope that nobody has a way to hack into SMM. Otherwise, virtualization security is gone. OK, one last point on this section is the micro VMMs. Micro VMMs are something that is becoming more and more popular recently. And the interesting thing about micro VMMs is that what they do is they sit underneath the operating system, and they allow the guest operating system to communicate directly with the hardware, what the red lines are showing. While at the same time, they are capturing a minimal set of events that they have to, which are the green lines. Now, micro VMMs are used for various tasks, but the most common one is security. One strong example for this would be the McAfee DeepSafe, the McAfee Intel cooperation that is actually used to do security protections, anti-rootkit, and this type of stuff on the CPU. Problem is, if you actually get to run inside the guest kernel mode, once you can access the hardware, you can fairly easily subvert the VMM. And we'll get to why this is a bit later, but this is the general idea. So just to summarize this section, there are many ways to use hardware virtualization technology. Type 1, Type 2, micro VMMs. You could para-virtualize or not para-virtualize. Each approach has its own unique challenges. If you do a full hardware virtualization, you need to secure a big implementation of software emulation for all the hardware that you're emulating. If you are doing para-virtualization, you created an interface between the guest operating system and the host operating system, so you need to secure it. If you, regardless which implementation you picked, you need to emulate the ISA correctly, which is a headache, and securely, which means no confused deputy type of situations. And finally, when you create a micro VMM, you have to defend from hardware subversion without going into full hardware emulation, which is really a problem. And finally, SMM has too many privileges, and there are no STMs. OK, so moving on, we're going to talk about memory. And everybody in this room, or most of you, I guess, know how computer memory works. You have an address, you have a value. It's very, very simple, right? Come on, address X, value Y. This is the diagram that describes the first diagram in the Intel manual that describes how memory works. This is less user-friendly, I think. So what this diagram actually says, let me show you a few highlights. First off, we have over there a value called TOM, which is top of memory, or the size of the DRAM. Then if we just look around, you get the EPUMA, which you don't know what it is, but it is a stolen range used for the chipset information, and Joanna Rostkowska as a chipset memory. Chipset firmware memory. Sorry, I had a problem there. Anyways, and then you get all the different areas like the OS visible range that is over 64 gigabytes. You get this interesting thing, this line over here. Anybody knows what this region is? This is the reclaim region. The region that is, if you remember back when we worked only in 32 bits, you had a limited amount of memory that if you bought more, you didn't actually get more memory for your CPU. The reason for this is this reclaim, this range that cannot be accessed by a normal operating system. Maybe I should explain this a bit better because I skipped one part of the explanation. Left-hand side represents how the CPU sees the physical memory. On the right-hand side over here, what you see is the way the DRAM controller, or the actual values that are stored in your DRAM chip. So what happens here is that memory that is accessed at this address is actually stored on the DRAM at a different address, causing a translation. Now, this translation was used when it was not locked to break virtualization systems, because the guest remapped some of its memory to point to memory that the VMM is actually residing in, and then overwrote the VMM code or data. And that's why they exploited the VMM. So nowadays, there is a lock register that is supposed to be used to prevent changing this after this is configured, assuming it is actually locked. I suggest everybody reverse their BIOS and check. OK, so, and finally, you get some really, really weird ranges. If there's anybody in this room that is able to come on stage and say what PPPE is, be my guest. I really want to hear. Because there are lots of secret ranges and undocumented ranges, and this one I found only in one Intel manual or two, and somebody has to tell me. Anyways, so moving on. Address translations are actually even more complex than we discussed so far. Because what we get here, we get actually at least 3 different translations in a healthy virtualization system. And these translations are first the paging translation, or page tables, which take a certain address and convert it to a different address. Then we get Intel came up and thought, oh, paging is great. Let's do extended page table, which is basically another level of paging, because that's great, right? We like it. So, we do again a paging translation. And then if we are unlucky, we fall on a certain special region or reclaim region, and our memory access is actually redirected to somewhere else. So basically, memory is not simple, and this is even before I started talking about cache and how searches in the cache are being made before you actually access the DRAM, right? The extended page table, I'll say another word about it. It's actually a very useful feature. The extended page table is a feature that allows the virtualization environment to virtualize the accesses that the guest operating system thinks already reached the physical memory, which means that when the guest operating system thinks that it's done, the virtual machine monitor can actually make a decision if this access is right for it or not, or where is it going, where does it want the access to go to. So it's a very useful feature when you want to secure something, but it's it adds a lot of complexity to the system, as you can see on the screen, which is kind of scary. So when we actually want to make a memory access, what actually happens? There are several types of memory accesses. So the green line in this diagram represents an access that is made from the CPU directly to the DRAM or to your RAM chip, right? This is the simple one. What happens when you have the purple line, when the CPU accesses a device? This is what's called memory mapped I/O, or a situation where you have a range of addresses in memory, and we'll get to it in the next slide a bit more, that is actually not used as part of the DRAM. It is redirected to one of your hardware devices, whether it's an integrated device like the PCA, something inside the PCH or the CPU, or an external device like your wireless LAN card, for example, or whatever else. And finally, a device might make a memory access, and this is the yellow line, and this is what's called the direct memory access, or DMA. And what's also interesting to know is that since some devices are nowadays integrated in the CPU, and the CPU has a way to directly connect to it the PCI devices, this is called processor-enhanced graphics, or PEG, then actually requests from devices could come along the big blue line instead of along the big red line. And in either case, all of these accesses must be monitored to not actually allow a guest to access either reconfigure hardware or overwrite anything that is critical for the VMM security, whether it's code, data, or structures that the VMM is relying on. OK. So the green highlighted areas are the MMIO, or memory mapped I/O regions. So basically, in this diagram, you get two, which is great, because this is not true. But the theory works like this. Everything that is MMIO should be, if it's below 4 GB, so it should be the last range before 4 GB memory boundary. Or if it's 64 GB, it should be the top of memory. This is the theory that Intel wants you to follow. AMD too, and I'm assuming that ARM has something similar. But the reality is different. The reality is that you can configure MMIO ranges are configured based on registers that are called base address registers. Once you configure the base address register of any MMIO device, you can put any value in there, and you can just decide to configure it, for example, right here, where TSEG, where SMM resides, right here on the low DRAM, let's say on the first megabyte of the memory of your machine to drive crazy or BIOS. You can configure it anywhere you like, basically. And this gives you an opening to create some interesting attacks if you have access to reconfigure the bar register, because you can just make it overlap anything you like and load data. Let's say let's say my memory mapped I/O region is actually representing the last packet my Ethernet card received, right? So I know the values there because I'm, I don't know, pinging it or sending packets to it, right? And at the same time, I change the place it is, the base address register, to make it overlap the code from, I don't know what, the VMM code, the code of my hypervisor. So at this moment, he will run from the code that is actually the last packet that arrived to the Ethernet card. Who understood me? Because you're too quiet. OK, so we can move on. Those that didn't, ask the guy next to you after the talk. OK. So in addition to having the memory mapped I/O, we have special address ranges. Special address ranges are ranges that have special functionality in the computer. For example, you have the legacy DOS area right here, the low memory addresses, each of which has a special function. You have the main memory addresses described here, each of which, and it is broken to different regions that also have special functions, and so on and so forth. I really don't want to get into this because this could be a whole talk on its own. But the general idea is you don't want to give anyone access to these regions, because when he has access to these regions, he can reconfigure your hardware and just subvert your machine under you. And finally, we could have talk about cache. As I mentioned, the SMM cache poisoning attacks. We can't really talk about I can't really find the time to talk about this and finish this talk in any reasonable way. I actually wrote the original version with a discussion about cache, and it took like 15 slides. And then I said, oh, damn it. So the bottom line, I'll just give you the short overview of these 15 slides. Cache is optimized for performance. Performance doesn't play well with security. You optimize for performance. You don't optimize for security. The end. Thanks. OK, so anyways, just to summarize this section, memory is complex. I think we can all agree on this now. Attackers with access to MMIO or physical memory addresses can compromise basically anything on the system. Access to special address ranges is also dangerous because it gives the attacker the potential to subvert your hardware by misconfiguring it. EPT can help mitigate some of these problems if you can configure it correctly and if it is available on your platform, which is a problem because EPT is only available on high-end hardware and not on low-end hardware. So you have to buy the more expensive CPUs if you want this protection, which kind of makes sense on the Intel side. But yeah. OK. So next off, I'm going to talk about the insights of computer platforms and how these affect the security. Yeah, and just wait my throat before I do. OK. So what is a computer? We talked about the fact it's a very complex device internally. We already talked about the fact that the logical software architecture can be complex. But the other thing that we should note is that every modern computer is a very high-speed, complex network of interconnecting components, each speaking in different protocols, using many buses or many types of networks, and passing data at an extremely high speed. So this diagram represents our CPU, more or less. How does it work? Basically, you have the big blue box on the outside, which is the CPU. CPU is actually broken into, let's say, 2 cores, right? Core 1, core 2. Each of these cores is, again, broken into 2 hyperthreads. 1 hyperthread, 2 hyperthreads. So basically, you get 4 logical processors within 1 CPU package. In addition, each core has some shared area and some stuff, for example, shared registers, shared cache area that is shared between both hyperthreads of this same core. And finally, there is another part that is called the anchor. Anyone cares to hazard a guess what's the definition of anchor? Go, man. Exactly. Everything that is not core. OK. So everything that is not core is the uncore. And what does this mean actually for us? It means the integrated devices, which include in modern CPU generations the integrated graphics. They include a special device that actually, several special devices that represent the CPU. And they include all sorts of things, other things like power management and things like this. Then we get the memory management unit or memory control hub that we saw when we talked about memory, which communicates with the RAM. And another component that we have is the processor-enhanced graphics that I mentioned, which allows PCIe devices to be connected directly to the CPU without going through the chipset, which is a great idea because now everything that is done on VTD to protect in the chipset needs to be done also in the CPU. And the interesting thing is it's processor-enhanced graphics. So you would think that only graphics card could be connected there. But no, you can connect any PCIe device you like. It's not like anybody's enforcing that it will be a graphics card. And finally, you get the DMI bus, which is actually connecting us to the next main component of the x86 or x64, the modern CPU computer architecture. So who knows what's the other major component? What's his name? Come on. No, you are wrong, sir. But you're on the right direction. Anybody else? That's right, man. OK, so the platform control hub is what replaced the South Bridge. And we used to have the platform used to be broken into 3 main chips. We used to have the CPU, the North Bridge, and the South Bridge. And it was a line that connected between them. But actually, the way it is now is that the North Bridge was broken into 2. Half of it was merged with the South Bridge and created the platform control hub, or PCH. And the other half was merged into the Encore in the CPU and became some of the integrated devices of the CPU. So the PCH is actually fairly complex internally, and this diagram doesn't do it justice. But what can I do? I can talk all day about architecture. So what we have here, the PCH is made from many internal devices, such as the LAN card, for example. The integrated LAN is in the PCH. Many bridges, many chipset power management, thermal code, and various other things. In addition, the PCH has several bridges. So one bridge is connecting all the PCIe devices to through the PCH. And another bridge, several other bridges, are connecting to different legacy devices. In this diagram, I only drew one, but actually there are several. One, for example, for the LPC bus, one from the SPI bus that contains the embedded controller in laptops, one for the, I don't know, various other low-speed buses that you can think of. And basically, when you talk about virtualizing the hardware, you talk about actually virtualizing all these devices. You need to actually create an emulation of these devices for your actual platform. Some of these devices are your keyboard or your mouse or the USB hub. Everything goes through the PCH, basically. Everything that talks to your CPU. And naturally, device virtualization is very simple. We can just use QEMU. Zen and KVM use a modified QEMU for their needs. And there are no vulnerabilities in QEMU, right? Yeah, so that was my quick search on vulnerabilities in QEMU. OK. So to solve the problem of actually how do we give access or protect situations where there is access to the hardware by a guest, what we want to do is we want to have the ability to virtualize the hardware in a similar manner to the way we virtualize software. And for this, we have the VTD, or Virtualization Technology for Directed I/O, which is called also IOMMU. And it is used for virtualizing the chipset components. So there are two main features for this technology. One is DMA remapping, and the other is interrupt remapping. So DMA remapping, as the name implies, is basically allowing you to perform paging or remap DMA access from devices to the DRAM to different addresses. And this is done by a paging mechanism, because Intel loves paging. We already had regular paging, EPT, and now we have VTD paging, right? And because paging is great, then they created the nested translation concept, which is the diagram on the top right over here, which allows you to perform 1, 2, 3, 4, 5, 6, 7 times 4 translations to get a single address. If you can configure this, call me. I need your help. OK. Anyways, interrupt remapping is a really, really nice feature, which allows you to remap the way interrupts are delivered to guests and to the VMM. And this is also a very important feature, because there were actual real-world attacks that did this. And a very nice paper on this is Following the White Rabbit by Joanna Rutkowska and Rafael Wuzczak. The interesting thing about interrupt remapping is that even in the latest generation of Intel CPUs, there is one known errata in interrupt remapping, which means that you can DOS a machine or shut it down if you have access to generate interrupts and certain configuration conditions exist. This is a work by a person called Gabor Peck, and I recommend reading it for those interested in the low-level details. And finally, what do you do with old systems where you don't have VTD? Or what do you do in systems where you have VTD, but it's an older generation? Even on your newest CPUs, you still don't have a fix for the Gabor-Peck errata. So VTD is not very simple. It's a spec that is still growing, and hopefully it will be stable one day. I suspect this is several years ahead of us still. So just to summarize this section, computer platforms are complex, and emulating the necessary components is hard. There are multiple CVEs already found in CV and the PIC virtualization, as well as QEMU. Actually, didn't get into ACPI and the PIC, but you can find it in my backup materials. And this will be uploaded. And VTD helps virtualizing the DMA hardware and hardware interrupts if it is used correctly. OK, so we're getting to the last part of this talk. We're going to talk a bit about different attack vectors, things that I didn't get to talk about so far. And then I'm going to get to the actual suggested VM escape. So first off, the most basic vector we can talk about is the ISA implementation. We talked about it. Emulating all the specification or even part of the x86 specification is not easy. Next off, another classic one would be performance monitoring. There are lots of performance monitoring counters, and we can use them to basically trace the way that program executes within the VMM and try to figure out or hack it this way. Real-time instruction tracing is a new feature that is coming up and might be very, very interesting in this context. Then we get to the problem of what do you do when your system is old? New defenses keep being introduced with the latest hardware. If you can identify that the actual hardware you're running on, and there is a very nice talk about different red pills, paper, not talk, about different red pills and how to automatically generate red pills that allow you to identify the specific hardware you're running on, then you can identify the fact that you're on an old system and use a bug that maybe is fixed on the newest versions, but it's just not fixed in the old hardware, and you can't fix it in the old hardware. That's the whole point of hardware. And then you get the new features. What do you do when a whole new CPU feature is introduced, like RT80 that I mentioned earlier, and it has some new register that is a buffer that writes directly to physical memory? Then you need to actually virtualize it, right? But if your virtualization engine didn't support it and now it is installed on newer hardware, then it doesn't know that it needs to virtualize it, and then either it doesn't give access to any new feature, which is a blacklist approach that kind of kills all the new features in your CPU. You can't get access to them. Or it gives access to every feature, and then it takes the risk that it is infected. Usually, bare metal hypervisors don't give access to any feature. So you get something like, for example, VMware Player. And as far as I can tell, the default in VMware ESX emulates a 440BX chip. Anybody knows from which year is this?
98.
Close enough, 97. So you get kind of old systems. OK, so another interesting thing is the I/O address space. The I/O address space is used to actually configure the PCIe devices and to directly communicate with them. You can write directly to disk if you just write to the I/O SATA port and various other things. So anybody knows how many I/O ports are in x86? Who said 64K? You're wrong. Another number?
4K.
No, you're wrong as well. 64K was closer, but you missed by how much? Anybody? No, 64K plus 3. Now, any idea why is it plus 3? Because the widths of when you access I/O ports, you can access 1 byte word, which is 2 bytes, or 4 bytes, right? And you can have as the base port 64K values. So you can start from port 0 to 65535. But if you access 4 bytes at 65535, then you get 3 unknown ports that are beyond 65535. You actually have 64K plus 3, which is kind of weird. Yeah. I'm disappointed in you guys. I expected someone to know this. Anyways. So the other interesting thing is that you can actually overlap ports. What happens if you overlap the keyboard port, which is actually configurable in some conditions, with the I/O configuration port, which is CF8? Or when you overlap the SATA hardware port with some of these ports, you get a problem in decoding that nobody knows how to actually answer. Some things are decoded, some are not. So this is an interesting case. We already talked about overlapping MMIO ranges in all different ways. There are special memory ranges we also talked about. And what happens when you overlap a special memory range with an MMIO range, or mix stuff together? It's fun. And finally, you get the model-specific registers, which we didn't get to talk about. But they are an interesting thing in and of themselves. They are actually the configuration registers of the CPU. They comprise a whole sort of address space. But the interesting thing is certain configuration registers don't actually deal with configuration. Certain MSRs actually trigger actions when you write to them. Sorry. So you might face something like an MSR that when you write to it, triggers the BIOS update. This is MSR 79 hex, or things like that. And if you give any access to MSRs, you risk, basically, your system. Finally, we get, not finally, actually. Corrupted ACMs are another problem. Anybody knows what ACMs are? Who said this? I heard you. You? Come by after the talk. OK. So the interesting thing about ACMs is that they are basically running, they are code modules, very small code modules, that are signed by Intel, and they are basically running in sort of unlimited privilege mode. If you have a bug in one that allows you to actually escalate to their execution mode, you can do whatever you like within the CPU. So not within the CPU, within any software, any physical address, whatever you are aiming at. Next off, we get the CPU and PCH firmware. And I'm not only talking about the microcode that implements the ISA. This is the one that everybody are aware of. But actually, there is something that is called the manageability engine, which has been hacked into several times. And it runs within the PCH. It's sort of the firmware of the PCH. And it has unlimited access to any physical memory address, which means that once you're there, you broke into anything on the system. In addition to this, graphics has its own microcode, the integrated graphics. Power control has its own microcode. And if you can break into one of them, good luck. You can have a lot of fun. And it is possible, although hard. Anyways, BIOS and SMM are also a common component of every platform and control both the configuration of the platform and have the privilege to access everything. So those are interesting attack vectors. And finally, we talked about intentional misconfigurations. You can take this to various places. You can misconfigure the PCI configuration space, MSRs or MMIO constants in order to create unexpected situations to the VMM, even to the emulation of these features. Usually doesn't handle these weird corner cases, because why should the emulation handle the weird corner case where a port overlaps a port? So in the case of I tried to do it to VMware Player, actually, because I thought I had a very quick attack on and demo for this talk. And it turns out that VMware Player actually detects this because it supports Windows 3.1, which had problems with this. So finally, Microsoft did something to improve the security of server platforms are really, really fun. I don't know if you're aware how Intel skews the platforms, but actually there are desktop platforms, which are basically everything inside of them. The actual microarchitecture is the same. Haswell microarchitecture, whether you get it inside your laptop or inside the desktop, is all the same. But when it gets to the actual microarchitecture, to the actual servers, they actually get skews. They are not the same. They have updates to their microcode. They have a ton of new features. And those features run at extreme privilege level. Highly recommended to look up the manuals and actually target them if you want to escape from virtualization, especially because if you are trying to do an escape from virtualization, you will usually be in a server farm. And therefore, this is something very nice to target. And finally, we get to CPU errata. So any virtualization, any code running on the system has to rely on the hardware performing correctly. But actually, the hardware doesn't perform correctly. Intel publishes errata on every CPU and updates it and updates it and updates it and so forth and so on. And practically, you need to think, where is the virtualization engine needs to rely on this specific function that I know that has errata, and then you can take advantage of it. And to demonstrate this, here's my bonus part, potential VM escape on any second-generation core CPU. So we have here an errata that says basically the following. If you go from 32-bit mode to 64-bit mode, load the 64-bit value to CR3, which is the memory paging root, the root of the paging structure, and then go back to 32-bit mode, then the CPU will continue to use the 64-bit value, which means that you can actually corrupt the pointer and point it to anywhere you like, while your virtualization engine thinks that it is in the lower 32 bits, because this is the size of CR3 when you're in 32-bit mode. So this is not something that operating systems normally do, because they don't transition to 64 bits and go back to 32-bit mode. But should you actually choose to do this, you can trigger this errata. Now, the problem is that if the virtualization engine actually writes the CR3 value along the transition path, then it will, if it writes a 32-bit CR3 value, this is the workaround. So, and it turns out, based on my correspondence with VMware, that they at least believe they handle this case. But I haven't checked on other virtualization platforms. OK, so that's that. Computer platform, just to summarize what we've talked about, computer platforms are complex. We've seen it, memory, architecture, and software stacks. There are several approaches to virtualize hardware, each with its own inherent weaknesses. Full hardware virtualization is slow and uses software emulation. Direct hardware access is prone to malicious hardware manipulations. And better defenses are available only with new and sometimes high-end hardware. But really, if you're trying to defend the virtualization, use new hardware. If you're trying to hack it, go back. Thank you all for listening. I'm open to questions.
Thank you very much. Any questions? Questions from the internet? Yes?
Well,
question from the internet. Shouldn't there be 64K plus 7 addresses in IO space since we are now in 64 bits?
you're saying that there are 64K plus 7, but there is no in or out 8 bytes in Intel architecture. We're talking about PIO, so it's only in, out, inward, outward, or in D-word, out, D-word. So it's 64K plus 3.
Any more questions? Yep. Number 2.
My question is there any hope?
Yeah. So,
basically, I'm asking you, do you know about any hardware development project which is aiming to develop secure hardware in a way?
there's lots of hope. We're making progress all the time. I think what I presented here is both the good and the bad, because we see that over time things progress, but new attacks come up, and this is the way the world is everywhere. It's too bad that in hardware we don't hear about these components most of the time, which is why I wanted to talk.
Okay, so we have thanks.
I have one other question. It's a bit of a presentation technical question. Why are the slides marked with confidential?
Oh, whoops. Thank you. The answer is company template. But now you know company secrets, so I have to kill all of you. Please line up. Okay. Any other questions? Go ahead.
Yep.
Maybe half an answer to the previous question. Intel SGX is upcoming, right? Software guard extensions. It has had a nice welcome on Invisible Things, and it looks good for now. I think they removed a lot of legacy stuff there, or rather circumvented that. But we'll see how good it holds up to when it's actually released. And the other thing is for virtualization, you don't need hardware virtualization. Hardware virtualization you need when you want to virtualize Windows, which you don't do it for security. For security, you don't use Windows in the first place.
So I'll answer in, you have two different statements here. If you want to talk about SGX, I'd love to. I was the head of product security for SGX until 3 months ago. So, and basically, SGX is really a great step in the right direction, because what SGX says is, instead of trying to secure the entire platform, let's secure a small part, a small island for each application or each thing that we want to protect, and deal with the rest later. This is one thing. The other thing is you don't need to use hardware virtualization. I think that binary translation-based virtualization is even worse than hardware in security.
You use power virtualization. I mean, you're right, there's still an interface. But the point is the interface is at the same level where the people are that are implementing the virtualization. So they know their stuff usually, or for the largest part. It's different. When you have hardware virtualization, you're breaking abstraction. Basically, the VMware or whoever is implementing your hypervisor, kernel programmers, they know the hardware, but they are not Intel. They are not processor engineers. They don't know all the bits, all the internal workings. The point of abstraction is that you don't have to care about that your software runs also if you have the newest, as you say, the newest hardware, an older version of the hardware, and that's why you should use power virtualization, which is actually, before there was the hardware extensions like Intel VT and AMD, there was power virtualization for Linux, there was an attempt for Windows. I think the primary reason for the hardware accelerated virtualization is that people wanted to virtualize Windows on servers.
I would say that there were a lot of reasons to do hardware-based virtualization, basically to be able to virtualize things without compiling support into their code, which is fairly important. I think that history shows that overall that power virtualization has had a lot of weaknesses, and basically it's very similar to the model of system calls, which we know work for privilege escalations into the operating system, even in 2013, even with all the modern protections. Now, I'm not arguing what you're saying. This is another approach which is useful, but nothing is foolproof, and you need to take the pluses and the minuses, and I'd love to continue talking. Just come on over after the talk, but I think the guy behind you wants to ask questions as well, so.
It's kind of on a related note. I think I remember reading about running applications directly on top of the hypervisor without a VM as such. Most of your talk was about how broad the attack vector is, and would that reduce the problems enough to consider it safe?
Yeah, but if you run applications, let me just be clear. You're suggesting to run an application in root mode? Sort of like in the kernel of the hypervisor?
Not in the kernel of the hypervisor, on top of the hypervisor. I'm not sure exactly how it was implemented, whether it has the ability to access the hardware itself or limited hardware. I'm not sure exactly how. It's a vague memory, and do you know anything about it?
I'm not familiar with what you're talking about.
This disaggregated Xen, for example.
Oh, disaggregated Xen?
Yes, the disaggregated Xen paper, which may be not exactly what you mean, but it's an effort to, disaggregate Xen, so to split Xen into multiple parts, because Xen basically has a trusted DOM 0, right?
You mean something like cubes OS?
Cubes? Do you mean cubes? Invisible things labs? Sorry, and the other part would be the L4 kernel that could run as a or this microkernel, which that also do virtualization at the same time. So they could run native tasks and at the same time also run OSSS tasks.
I'm sorry, I failed to understand the definition here. Please come by, I'll give you my email and we can talk about this much as like.
All righty, any final question? If not, I suggest we give Mr. Deskin a warm applause.
Thank you, everyone.